All right, so this week we'll finish up with section 3.5, which is on kind of what we've done the past 2 days. It's on solving equations, finding the roots, but now the answers might be complex. Okay? But all the stuff we already know, synthetic division, rational root theorem, all that stuff still works. So we'll do a very quick overview of complex numbers, and then we'll go into using how we find roots with complex numbers. Okay, so just a reminder that if c is a zero of a function, it means that you plug it in for x and you get 0 for y. So that's the place where it crosses the x-axis. So if I said to you 2 is a root of the function, that means the x-intercept is at 2, 0. It's where it crosses the x-axis. So, every function has things you can plug into it to make them 0. Sometimes the thing you plug in is a real number. Sometimes it's not a real number. So if you graph something like a parabola, and it looks like that, it never crosses the x-axis, but that doesn't mean there isn't a root. It just means there isn't a real root. Okay? So this parabola would have 2 imaginary solutions. So this equation I have right here, that could represent that parabola. This is a parabola shifted up 1. And that's kind of what my picture is showing. Now, with real numbers, if you square something, what kind of number do you get if you square something? You always get, could be this or higher.
You always get positive.
Positive or
0.
0. Okay? Anytime you square something, you always get a 0 or higher. You never get a negative. Well, if you take something that's 0 or higher and you add 1 to it, are you ever going to get 0? No, it's impossible. You can't take a number that's 0 or higher and add 1 and get 0. So the answers to this equation would have to be imaginary. Okay? And the way we would solve it, get all the x's on one side, they already are. Subtract your 1. And then how do we undo squaring? Yeah, we take a square root. Square root, square root, and there's your answer. And that's what we're going to talk more about. Okay? The answer is the square root of -1. There is a way to simplify that. And technically it's both the positive square root of -1 and the negative square root of -1. Does anybody know what the square root of -1 is? What?
I.
Yeah, it's I. Do you know why?
No.
It's kind of a trick question. I won't explain why in a second. There's really no way I can explain why. It's a definition. So that answer that we just got, square root of -1, it's I. That's just the way it is. It's kind of like if you were doing geometry and somebody said, prove to me why parallel lines don't cross. You can't. That's just a concept, and that's just a building block for geometry, and we just assume that's true. It's a definition. Same idea with this. Okay? We got to come up with something to represent the square root of -1, and they chose to use the symbol I. But remember, I is just a symbol. Yes, it's an English letter, but it stands for the number square root of -1. Just like that's a Greek letter, and it stands for the number 3.14. Okay, so really it stands for a number. That's what I is. So if we took I and squared it, anyone think they could tell me what that would be? I squared, yeah?
-1.
I squared would be -1. Because if you square the square root of -1, the square and the square root cancel, and what you're left with is what's underneath the root. That's all you're left with. And that's important because we're going to do some problems today that I squared is going to come up. So anytime you get an I squared, change it to -1. Try to make my 1's and I's clear. So let's look at what happens if you plug I in for x in the equation we just looked at. You would get I squared plus 1. And Cassandra, what's I squared? It's negative 1. So we have negative 1 plus 1. And Rue, if I do negative 1 plus 1,
0.
I get 0. So that means I is a root. It's one of the roots of this equation. The other one is negative I. Okay, so any questions on that? That's kind of the idea of what we're going to get to. You're going to be given an equation, and you're going to have to figure out the roots. But before that, we just have to go over really quickly like the basics with complex numbers, the arithmetic, and then we'll get into the kind of problems that was similar to yesterday. Okay, so quick overview of complex numbers. So complex numbers are written in the form a plus bi. Okay, a is the real part, b is the imaginary part. Okay, here's an example of a complex number exactly in that form. 2 plus 3i. 2 is the real part, 3 is the imaginary part. Now, since complex numbers are made up of a real part and an imaginary part, sometimes one of those parts is 0. Like in the number 3i. There's no real part. You could think of it as 0 plus 3i. No real part. Same thing with negative 7i. There's no real part. We're kind of the flip side to that is the number 4. Think of that as 4 plus 0i. There's no imaginary part. So technically, every single number you've ever studied is a complex number. Sometimes it has a real part, sometimes it has an imaginary part, sometimes it has both. Okay, but everything kind of fits under that umbrella of complex numbers. So any question on the difference between a complex number and a real number or an imaginary number? It's kind of important to understand. And some more examples. You don't need to write every example. So the idea of equality. So this is just emphasizing that complex numbers have 2 parts, and you can't forget that. For 2 complex numbers to be equal, both the real parts and the imaginary parts have to match. Both the real parts and the imaginary parts have to match. So for example, 2 plus 3i would be the same as 2 plus 3i. 2 plus 3i would not be the same as 2 minus 3i. In that case, the real parts would match, like 2 and 2, but if one of them is a plus 3i and one of them is a minus 3i, they're not the same complex number. So we're going to look at basically the 4 operations you can do with complex numbers. Add, subtract, multiply, divide. And when you're adding or subtracting complex numbers, you can treat I like a letter. I want you to remember, though, it's not a letter. It's the number square root negative 1. But for thinking about it in your head, like if you wanted to do 2i plus 3i, it's 5i. Okay? It's the same idea as like 2x plus 3x, 5x. But remember, I is not a variable. Okay, any question on that? Okay, I is not a variable. Okay. When we multiply complex numbers, the idea of FOIL, or a double distributive property, is going to come up. And when you do that, you're going to get some I squareds. So anytime you have a problem with an I squared, make sure you make I squared negative 1. When we divide complex numbers, we're going to have to use the idea of conjugates. And we'll go through one of each of these. when you divide complex numbers, we're going to have to use what's called a conjugate. And we're going to also have some problems with square roots. This could come up when you do quadratic formula. So if you had an answer in quadratic formula, say you had 2 plus or minus square root negative 7 over 3. But you don't want to leave it as square root negative 7. So we're gonna look at how we simplify that. So it could be square root of negative 7, negative 12, it doesn't matter. Square root of negative something. When you have the square root of negative x, what number is in front of the x? Yeah, it's a negative 1. So you could think of it like that. And we did exactly the same thing when we reduced square roots. It's almost like you have factored the square root, kind of like this. And now once you factor it, you can break it up and take the square root of each thing separate. Square root 4, square root 5. Square root negative 1, square root x. And then once you break it up, one of the roots you can usually simplify. So in this case, what's the square root of negative 1? What does that simplify to? Yeah. Simplifies to I. So basically what happens is anytime you take the square root of a negative, you take an I out. Now, where you put the I kind of depends on what's in the problem. If you just have something with a number and an I, we usually put the I after the number. 2i, 5i, things like that. But if you had a square root, I would not do something like this. I would do it like that. Why do you think the way on the right is clearer than the way on the left? Something confusing about the way on the left. Really?
Because it looks like I is still underneath the square root symbol.
Yeah, it kind of looks like the I is under the square root symbol, and it definitely shouldn't be. So if you just move the I in front, then you can make that as long as you want, and there's still no confusion. It's I square root 5. Okay, so when you have the square root symbol, get used to putting the I in front. If you don't have a square root symbol, it's perfectly fine to put it after it. I guess even technically here, you could put I3, but we don't normally do that. Okay, so let's try simplifying some of these. Okay, let's start with square root negative 4. You don't have to show all these steps. Okay, if you can just give me the answer to square root negative 4, that's fine. So Chantal, do you think you could tell me what square root negative 4 would be?
2i.
2i. Yep. And you put the I after the 2, that's perfect. There's no confusion. How about square root negative 9? Yep.
3i.
3i. Okay. How about square root negative 7? Dan? Perfect. I square root 7. And square root of negative 20. So you have to do what you would if it was square root 20, and then just put an I with your answer. Yeah?
2i square root 5.
Yeah. So normally this would just be 2 square roots of 5. But that I also has to come out, so we put 2i square root 5. Perfect. Okay, so any questions on that idea? Okay, again, you'll see that when you use quadratic formula. You might get a square root of a negative. Now we'll go through one each of add, subtract, multiply, divide, and then we'll be done with the review part. Okay, when you're adding and subtracting complex numbers, think of it as combining like terms. You can combine real parts with real parts. And you can combine imaginaries with imaginaries. So let's do that and see what we get. So we've got a real part of 7 plus a real part of 4. So my final answer, Scott, what's going to be the real part?
3. Or were you adding it? Sorry. 11.
11. Yeah, if you were subtracting, it would be 3. So 11. Then we have a negative 3i plus 5i. Yep. Negative 3 plus 5 is 2i. And that's it. That's your answer. All answers should always be written real part, imaginary part separate. Just like that. Any questions on that one? Okay, don't make the mistake on this one and do FOIL. Okay, we are going to do one like that right here. But there's a big difference if you put a plus sign between them or you don't. Okay, let's try this one. This one, you do want to think of that negative as being distributed. Because you're not only subtracting the 6 from what's in the parentheses in front of it, you're also subtracting the I. Okay, so let's try that. So how about, Nick, what's going to be my real part here?
Negative 2.
Perfect. 4 minus 6, and my imaginary part?
Negative 3. Or minus 3.
Minus 3. Yep. Minus 3i. So negative 2 minus I. It's very similar to addition. Just remember that that negative applies to both terms. It's usually one mistake people make. Okay. Questions on that? Let's go to multiplication. Now multiplication is where you're going to do the distributive property twice, okay, or a FOIL. All right, so when we do FOIL, Tanner, what would be the first two things we would multiply? All right, so first thing, if you're doing, you follow FOIL, what's the first term in each set of parentheses?
2 and 5.
Yeah, so let's do 2 times 5, which gives me
10.
10. Okay, so we got 10. Jess, what would be the next thing?
3i times 5. Or no, I mean 2 times negative I.
Yeah, you gotta multiply everything times everything. As long as I guess you do it in whatever order, but I'll just stick with first, outer, inner, last. So 2 times negative I is negative 2i. Malin, what would be next?
3i times 5.
Perfect. And what's 3i times 5?
15i.
15i. And now the last one is positive 3i times negative I. First, what's a positive times a negative? It's a negative. And then 3i times I. Devin?
Would be negative 3i squared, but I squared equals
Yeah, exactly. Yeah, we got to deal with that too. We don't have to deal with it all at once on the first one, but yes, we do. So we get negative 3i squared. Now we have 10 plus 13i. And then minus 3i squared. Devin, what did you just say I squared was?
negative 1.
Negative 1. Okay. So I have minus 3 times negative 1. Felipe, what's negative 3? Or minus 3 times negative 1? So...
Oh, positive 3.
Yeah, positive 3. Yeah, sometimes it looks a little confusing. So that minus and that minus just cancel out and we just get a plus 3. And now you can combine the 3 with the 10. Give you a chance to redeem yourself. What's 10 plus 3?
13.
Very good. Okay, so we get 13 plus 13i. Okay, so we got 13 plus 13i for that one. Now let's look at division. So first thing we have to look at when we do division is the idea of what's called a conjugate. Has anybody seen that term before, or know that term? So conjugate is something that's going to come up not just when we do this, but it's going to come up again when we get to trig.
Don't you conjugate verbs, Mr. Hager?
Yes, you do.
In foreign languages?
Yes, you do. Very good, Mishna.
I'm done now, but don't ask me about math.
Okay. So, conjugate basically in math, the way we're dealing with it, it's the idea that if you have A minus BI, the conjugate is when you change the sign of the imaginary part. So the fancy word for that is negate. So if you have A minus BI, your conjugate is A plus BI. So you don't do anything to the real part. You just change the imaginary part. Right, so what we're going to do is just practice finding a few conjugates. This should be pretty straightforward. So if you had 3 plus 2i, anyone think they could tell me what the conjugate would be? Yep.
3 minus 2i.
Perfect. 3 minus 2i. What about if you had 4 minus 5i? Yeah.
4 plus 2, 5i.
4, can you just say it again?
4 plus 5i.
Perfect. 4 plus 5i. 3i. What's the conjugate of that? Yeah?
Negative 3i.
Negative 3i. And what about 6? Dan? Just 6. It stays the same. If you're like, well, wait, why does it stay the same? Think of it as 6 plus 0i. There's no imaginary part. The conjugate is 6 minus 0i. Same thing. Okay, so any question on how to find a conjugate? All right, now we can finish up with the review of complex numbers and do a division problem. And then after this, the rest of today is going to be very, very similar to what we did yesterday. We're going to find roots. All right, so how do you divide two complex numbers? The way you do it is you multiply both the numerator and denominator of your complex number by the conjugate of what's in the bottom. Not the conjugate of what's in the top. That won't help at all. It's the conjugate of the denominator. And you'll see why we use the conjugate and why we do this. But a hint is that anytime you have a complex number, you can't leave it in the bottom of a fraction. Just like square roots. You can't leave square roots in the bottom of a fraction. You're not supposed to leave I in the bottom of a fraction either. So somehow what we're doing, technique I'm telling you, it's going to fix that. You'll see how in a second. Okay, so Ariana, my problem is 5 plus I divided by 2 minus 3i. What am I going to multiply top and bottom by?
2 plus 3i.
Perfect. I'm going to multiply by 2 plus 3i over 2 plus 3i. Okay, so now at the top, when we do it out, we get 5 times 2. And then Cassandra, I get 5 times 3i, which is 15i, plus 2i, which is how much?
17.
So we get 17i. And Rue, we have I times 3i, which is what?
3i.
3i squared. And if we simplify that, it would turn into perfect, negative 3. So we'll finish up the top in a second. Let's look at what happens in the bottom. So we've got 2 times 2, which gives me 4. Now, if I do the outer and the inner, okay, watch what happens. All right, so we did 2 times 2, we got 4. What's 2 times 3i? Yep.
6i.
And what's 2 times negative 3i?
Negative 6i.
So when you combine those, what happens?
Cancel 0i.
Yeah, they cancel, 0 out. So anytime you're multiplying conjugates, you never have to worry about the outer and the inner because they're always going to cancel. The only products you really need to do are the first and the last. So Scott, let's do the last. What's negative 3i times positive 3i.
Negative 9i squared.
Yep. So we get negative 9i squared, and when we fix the i squared, that would give us
9.
just a 9. So really, there's a shortcut for doing the bottom. You don't have to FOIL it. You can do what we just did every time. Or just take the first number and square it. Take the second number and square it, and add the two together. It doesn't matter if you square 3 or negative 3, you still get plus 9 either way. So just take the first number, square it, take the second number, square it, and add them up. If you don't like the shortcut, then just do it the way we did the first time. Alright, so now we can combine like terms. We're going to get 10 minus 3 is 7, plus 17i over 13. Now, technically that's not standard form. Standard form, real part, plus or minus, imaginary part. We need to figure out what goes in those two boxes. So we're just going to split that fraction up. So my real part is 7/13. In this case it's plus, and my imaginary part is 17/13. And usually we put the I in the middle. It's kind of like when you do slope-intercept form. Usually you just put the x in the middle. You don't have to. I mean, technically you could put the x in the top. It's not wrong, it's just not how usually we do it. Same thing with I. Usually put it right in the middle. Okay. Any questions on that? Great. So that's it for the reviews. That's add, subtract, multiply, and divide. The most important thing out of those is knowing how to multiply. Okay, because multiplying covers combining like terms, which is adding or subtracting. You're not going to have to know division specifically for finding roots, but you are going to have to know multiplying. Any question on how to do division? If I just ask you its own separate problem on the test. Okay. So now we'll just get into finding roots. And keep in mind now your answers could be real or imaginary. Tyler, what kind of equation is that based on its degree? Perfect, it's a quadratic. So do we have a method for solving equations that are quadratics? What's one? Well, actually we have a few. What's one way you could solve a quadratic? You could use quadratic equation. Do you remember another way? Or you could use factoring. This doesn't factor. Okay, so you can't find two numbers that multiply to give you 1 and add to give you 1. It's not going to work. So let's try factoring and see what happens. Let's try quadratic formula. Brooke, what's A, B, and C here?
1, 1.
Yeah, they're all 1. 1 and 1. So fill it into your formula. Negative b plus or minus the square root of b squared, 4ac, all over 2a. Okay, so I get negative 1 plus or minus, what's going to be under the square root? Okay? Negative 3 over 2. Now that's almost my answer, but I just don't want to leave the negative under the square root. So how would we rewrite it? So that we have an I in there somewhere instead of negative 3. Yep, Chantal?
Negative 1 plus or minus I square root 3 over 2.
Perfect. Yep. Negative 1 plus or minus I square root 3 over 2. And those are your roots. And because it's a quadratic, and I'm going to mention this again later, quadratic is degree 2, you got 2 answers. That should always happen. Any questions on that? One thing I should have mentioned before we even started, anytime you want to solve a quadratic, you have to get all the x's where? All the x's and the constant. They all have to be, yeah?
On the same side.
They all have to be on the same side. And they were. Okay? So in other words, it's equal to 0. If it's not equal to 0, put all the x's and the constant on the same side first, and then it will be. So, if you look back at the problem we just did, the two answers we have are conjugates. -1 plus I root 3 over 2, -1 minus I root 3 over 2. Those are conjugates. And in fact, that always happens, okay, which is kind of nice about complex roots. So if I give you a problem and I tell you that 1 plus 2i is a root, you automatically know 1 minus 2i is a root. Has to be. That's just how it works. Now, that idea doesn't really help you too much with real numbers, because in that case, the imaginary part is 0. And that would be like saying, if 6 plus 0i is a root, then 6 minus 0i is a root. It's the same thing. So, this idea doesn't help you with reals, but it does help you when the imaginary part is not 0. So any questions on that? So based on that idea, if you were solving a problem, could you ever get an odd amount of imaginary answers? Nick? No. Imaginary answers always occur in conjugate pairs. So if you've got 3, then you got another one, you got 4. Okay, you can't have 3, you have to have 4. Okay, so everything we did yesterday still works. Remainder theorem, factor theorem, synthetic division. Okay, and I'm going to show you right now a problem with synthetic division. Now, when we use synthetic division, we're not directly proving that the thing here is a root. What else does this mean? If 1 minus 2i is a root, we've said this a few times, what else does that mean? Yeah?
That 1 plus 2i is a root?
Okay, it does mean 1 plus 2i is a root as well. That's good. But I'm thinking about what's another way of saying 1 minus 2i is a root or 1 minus 2i is a 0. Don't say it's an x-intercept, because it's not. That doesn't apply here. But yeah, Nick?
That's a factor.
What's a factor?
1 minus 2i would be a factor, or would that be
Well, factor has to have x in it somewhere.
x minus 1 minus 2i?
Exactly. X minus that is a factor. So what we're going to prove is that x minus our root is a factor. And if we get a remainder of what? What are we hoping for?
0.
We're hoping for a remainder of 0. That proves it. Okay? And then if that's a factor, then whatever came after the minus sign is automatically a root, because they mean the same thing. Okay, so let's set it up. Take what's after your minus sign, what you'd have in the parentheses, put that on the outside of your synthetic division. And now copy down your leading coefficients. Make sure you leave any zeros for things you're missing. So 4, 0, 17, 14, 65. And it doesn't start out too bad. Okay, first couple steps are pretty easy. Okay, what's my first step? Chantel?
Bring down the 4.
Yep, bring down the 4. And now multiply 4 times 1 minus 2i. And that's not too bad because it's not a double distributive, it's just a single distributive. Okay. So what's 1 minus 2i times 4? Yeah.
4 minus 8i.
Yeah, it's going to be 4 minus 8i. Now you add it to what's above. That's still not bad. You're just adding it with 0. You get that. Now you need to multiply 1 minus 2i times 4 minus 8i, and then put the answer right there. So what I'm going to do to just keep the problem kind of nice looking is do it off to the side. 1 minus 2i times 4 minus 8i. Dan, what's 1 times 4? 4. And then I'm going to get a negative 8i, and then another negative 8i. So what's negative 8i plus another negative 8i? Yep, negative 16i. And how about Mei-Ling? Negative 2i times negative 8i.
It would be negative 16 times
Careful.
Oh, wait, it'd be positive.
Yeah, it'd be positive 16i squared, which would then be
Negative.
negative
Oh, then negative 16.
negative 16. So we get 4 minus 16, which is negative 12, minus 16i. Now the adding isn't bad because you never have anything to do with the imaginary. That just stays the same. But what's 17 minus or plus negative 12? 5. Okay. So now we'll do it one more time, and then the last time I'll just tell you what the answer is. So now we need to do 1 minus 2i times 5 minus 16i. So Jess, 1 times 5 gives me 5. And then I have negative 16 minus 10.
Negative 26i.
Yep. Negative 26i. And the last part, negative 2 times negative 16. Start with that.
32i squared.
Yep, so 32i squared. And Devin, can you tell me what 32i squared simplifies to?
Negative 32.
Perfect, negative 32. And we end up with negative 27 minus 26i. Okay. And negative 26i stays the same. What's 14 plus negative 27? Negative 13. Now, does anyone need me to do it the last time, or you just trust me what you'll get for that? Anyone need to see it one more time? No? You'll get negative 65. When you multiply this all out, all the i's are just going to cancel. Kind of look at it like you have a 2i times negative 13. That's going to give you a positive 26i. And then you have 1 times negative 26i, so there's your negative 26i. Okay, so it just cancels out, and we get a remainder of 0. So we have proved that 1 minus 2i is a factor. I'm sorry, x minus what I just said is a factor, or 1 minus 2i is a root. Now, if 1 minus 2i is a root, what else is a root? Scott?
Conjugate of it.
Yep, the conjugate of it, which would be?
1 plus 2i.
Exactly, 1 plus 2i. Okay, on a test, I would probably cut off a column of this. Probably wouldn't give you a 4th degree. I might give you like a cubic to do it with. So it would be one less round of multiplying. But that's why we went over multiplying complex numbers. Okay, I think this is a question you probably could have answered before I even explained stuff today. Why do odd degree polynomials have to have at least one real zero? Ted?
It would just go up and down forever, so that's across the x-axis.
And what kind of functions are they? I agree, they go up forever, they go down forever, but I could give you a function that goes up forever and down forever and never crosses the x-axis. They're continuous, exactly. So because it's continuous and it goes up forever and down forever, it's going to automatically cross the x-axis somewhere. So, knowing that fact, you know that this function, it's an odd degree polynomial, is going to cross the x-axis somewhere. And let's assume I'm being nice, and I gave you a problem that it's going to cross at a nice spot. How could you generate a list of numbers that would give you possibilities of where it would cross? What theorem could you use? Yeah?
Rational root.
Yeah, let's use the rational root theorem. Now, if you remember how to factor a difference of two cubes, you could actually do this problem a lot faster than we're going to do it. But I'm guessing people don't remember the formula for the difference of two cubes.
It was 2 years ago, I don't remember.
Ian, remember it? Okay, so again, you might not always have a difference of two cubes. Like if I gave you a problem like this, it would be totally different. So we'll just use the approach that would always work. Okay, rational root theorem. All right, what are my factors of p in this case? Yep.
Plus minus 1.
That's it, plus or minus 1. What are my factors of q? Same thing. So now, if we take all the p's and divide by all the q's, what would be all my possible rational roots? Dan? That's it. Plus or minus 1. So now I'm going to graph that. And because this problem is pretty straightforward, you could probably plug in 1 and negative 1 and see which one works before I even type it in. Okay, but it might not always be that easy to figure out, so we'll graph it. And which one seems like the likely one? 1. Yeah, it is 1. So, now that we know 1, and then we can double check it, 1 is a root. What do I do now to get the other two roots? Well, what else does that mean? If 1 is a root, that means that it's also a 0. It's also an x-intercept. But what's the other thing it means?
X minus 1 is a factor.
X minus 1 is a factor, so we've started to factor this. Okay, so x cubed minus 1 equals x minus 1 times something else. How do you figure out that's something else? That's what we need to know. Yeah? Yeah, we do the synthetic division, and then it's going to be the what of that?
The quotient.
Exactly, it's going to be the quotient. Okay? So just like we did, just like we said in the homework, same idea. So I'm going to put a 1 on the outside, and I'm going to divide x cubed minus 1 synthetically. So I have x cubed. Did I have an x squared term? X term? No. Okay, so bring down our 1. 1 times 1, add. 1 times 1, add again. 1 times 1 is 1, remainder 0. So here is my quotient, x squared plus x plus 1. So we just factored it. So we already know the answer to this part. Okay, so my roots, 1. And do we know the roots to x squared plus x plus 1? We just did that problem. X squared plus x plus 1 was this problem. We already set it equal to 0, and we already went through it. So these are the other two roots. Negative 1 plus or minus I root 3 over 2. So notice how many answers we got. 1, and then the two complex answers. And the highest exponent was a degree 3. So you always get as many answers as the highest exponent. and I count a repeated root as another answer. So like let's say you had x minus 2 as factors. You have 2 as a root, and you have 2 as a root. That's two answers. They're just not unique. So the problem we just did, that's the equation we just solved. If you want, you could rewrite it like this. Just add 1 to each side. Okay, so you could say 1 equals x cubed, or x cubed equals 1. So if you think about it this way, instead of thinking of rational root theorem and all that stuff, how do you get rid of cubing something? Yeah?
You cube root it.
You cube root it. So basically what we just did in the last problem, even though you didn't think of it this way, is we found all the cube roots of the number 1. And sometime in the book they refer to the number 1 as unity. That's what they call it. So the answer to that question right there, what are the cube roots of 1? It's the answers we just got in the last problem. When you're finding a root, your problem is going to have as many answers as the root would take you. If I asked you to find the 5th root of something, how many answers would you get?
5.
You'd get 5. Yeah. I wouldn't ask you to do probably anything more than that, because then it can get a little time consuming. The idea is if you set up this equation, x to a power minus 1 equals 0, just like we had right here. X to a power minus 1, all on one side, equals 0. You're basically finding the nth roots of 1. Okay, so in the next problem, I'm going to step it up 1 degree, and instead of finding the cube roots of 1, we're going to find the 4th roots of 1. Now, before we do it, how many answers should we expect? 4. Yeah, 4 answers. Okay. So we're finding the 4th roots of 1. 4. That's what goes in right there. 4th roots of 1. And the reason you set it up that way, because if you think about adding 1 to each side, you would have that, and then you would solve it by taking the 4th root of each side. But if you try to take the 4th root on the calculator is only going to give you 1 answer. It's not going to give you the other 3. That's why we set it up this way. Now, you could try your rational root theorem, you could do your P's and Q's and all that, but this actually factors. If you can factor it down to a quadratic, you can avoid synthetic division, rational root theorem, and using a graphing calculator. Does anybody see how x to the 4th minus 1 factors? Yep.
X squared minus 1, x squared plus 1.
Yep. It factors as x squared minus 1 and x squared plus 1. And now, out of those 2 factors, you can actually factor one of them a little more. Anybody see which factor you can factor into? One more step.
X squared minus 1.
Yeah, how does x squared minus 1 factor?
X plus 1, x minus 1.
So now you've got x plus 1, x minus 1, x squared plus 1. Now, just set each of those factors equal to 0 and solve. Okay, so we get x plus 1 equals 0, x minus 1 equals 0, x squared plus 1 equals 0. What do we get when we solve the first one?
-1.
Yep, -1. What do you get when you solve the second one?
+1.
+1. That's the one answer that the calculator would have given you if you did the problem taking the 4th root. It's the only answer you would have gotten. And here I need to subtract 1 from both sides. And what would be my last step there?
Well, you would square root it, and then the answer would be I.
When you take the square root, what do we have to be careful about? Remember, we should have 4 answers here. So you said
Plus
I,
or minus.
plus or minus, just like the quadratic formula. So I agree, it's going to be I and negative I. So there are your 4 answers. 1, negative 1, I, negative I. And it turns out if you graph those answers on the complex plane, they're all evenly spaced. They would look, I'm not going to get into this too much, but if you were to graph them, real axis, imaginary axis, that's how you do it. Real number 1, real number that's negative 1. Up 1 on the imaginary, 1i, down 1. All the answers are evenly spaced on a circle. That's the way it works. Any questions on that? All right. So, I'll come back to that statement in a second. But this statement is actually a little weaker than the one I have right there. This statement just says that if you have any polynomial with a degree greater than 0, so in other words, 1 or higher, you have a polynomial that's degree 1 or higher, then I guarantee you can find at least one thing you can plug in to make it 0. That's what the fundamental theorem of algebra says. If you have a polynomial that's degree 1 or higher, guaranteed you can find at least one thing to plug in to make it 0. And by one thing, that thing is a complex number. Remember, complex doesn't mean it has to have I in it. Everything is a complex number. That's just the big kind of umbrella category. But the statement above is even stronger, because all this says is if you've got a polynomial with degree 1 or higher, you can find at least one number to plug it in for 0. The statement above tells you exactly how many. It doesn't say at least. This statement up above says if you have a polynomial of degree n, you will find n things to make it 0. Exactly n things. So the total number of zeros always equals the degree of the polynomial. Okay, and the other idea is factoring. So if you have a quadratic, Devin, what's the degree on a quadratic?
2.
2. And when you factor it, how many sets of parentheses do you have? 2. So basically, the linear factorization theorem says that whatever the degree is, that's how many sets of parentheses you would have when you factor. And again, those factors do not need to be unique. Okay, and I write that down in a second. So if you had a cubic, well, Brooke, if you had a cubic, how many sets of parentheses would that factor into? 3. Exactly. So there's a cubic, and that's the factorization for it. Okay, at this point, you should feel pretty comfortable that you could figure that out. How would you figure that out if I asked you to factor x cubed minus 7x minus 6? What would be the first thing you would do? Yep. I agree. You're going to have to do synthetic division, but you wouldn't know what to use yet. So you have to do something before that. With the p and the q, you'd have to do the rational root theorem, generate a list of possibilities, and then use your calculator to narrow that list down, and then use synthetic division. And then once you use synthetic division, you would confirm that you have a root. And what would you focus on after the synthetic division? Focus on the quotient. That quotient would be something like if you divided through synthetically by, say, something to get the first factor, your quotient would be x squared minus x minus 6. That would be the quotient when you do synthetic division with a negative 1. Okay? So factors don't need to be distinct, I mentioned that. What would be the degree on this polynomial? What did it come from? Dan? Yeah, that's a degree 5. It's a degree 5 with only 2 roots in it, so it's only going to cross the x-axis twice. Are there going to be any imaginary roots in that degree 5 polynomial? Root, what do you think?
No.
No. Because in a degree 5, you can only have 5 answers, and I can see all 5 answers. -1, -1, 2, 2, 2. They're all real. So we've called -1 a double root. You can call it that, it's a double root. Or you can say it's a 0 or a root of multiplicity 2. That just means the root occurs twice. 2 is a root of multiplicity 3. It occurs 3 times. I think I'm going to skip that one, yeah. Okay, any questions on? Okay, so the last problem I'm going to do, I think they assume, because they give you one like this in the homework to do, but I don't necessarily think everybody would 100% know how to do it, so I'm going to show you one that's similar to it, and see what happens. Okay. What if I said, I want you to come up with a degree 2, and I want the roots to be 2 and 5. I want you to come up with a second degree polynomial with roots 2 and 5. How do you do that? Yeah, Felipe?
Well, first you change it to x minus 2 to x minus 5.
Okay, so if 2 is a root, then I know x minus 2 is a factor. And what else did you say?
X minus 5.
X minus 5. And now? Just multiply it out. So you get x squared minus 7x plus 10. Okay, not too bad. Any question on that? Okay, so now I want to do the same thing. Let's come up with a degree 2. This time I want the roots to be 1 plus 3i. And I'm not going to tell you the other root. What is the other root? Even though I didn't tell you, you have to know what it is. It's the conjugate. So if I don't tell you the other root, you have to know it's the conjugate. And actually, I'm going to write it separate. You don't have to, but there's a reason why I'm doing that. I'll show you in a second. So now, if 1 plus 3i is a root, what is a factor in this case? Exactly. X minus that. And what would be my other root? Oh, what would be my other factor? Yeah, Jess?
X minus 1 minus 3i.
X minus 1 minus 3i. You do exactly the same thing. It's just for some reason people seem to get confused when you throw the complex number in there. But it's no different. And then when we start to do it out, we have x minus 1 minus 3i, x minus 1 plus 3i. Okay. And if we do this right, all the i's should cancel out. We're going to get some funny terms in there, and like funny terms, I call them ix terms. Like you're going to get a 3ix at one point, but hopefully that should be canceled with a negative 3ix at some point. Okay. So let's do it out. Cassandra, what's x times x? X squared. X times negative 1. And then x times 3i. 3ix. Okay, we're going to hope that 3ix goes away. Rue, what's negative 1 times x? Negative 1 times negative 1. And negative 1 times 3i. Negative 3i. Okay. And now, let's multiply out negative 3i times everything. How about, Abby, what's negative 3i times x?
Negative 3i.
Yep. So we got that one. Negative 3i times negative 1 is positive 3i. And then negative 3i times positive 3i. That one doesn't cancel. You're going to get negative 9i squared, but then we got to fix it.
That would be positive 9.
Positive 9. Okay, now let's look through and see what cancels. Anybody see one thing that's going to cancel out? Scott?
Positive and negative 3ix.
Positive 3ix. Negative 3ix. Anything else? Yep, Tyler.
Positive 3i.
Negative 3i, positive 3i, and now look, all the i's are gone. So just combine like terms with what you have left. X squared. What's my x term going to be?
Minus 2x.
Minus 2x. And my constant? Plus 10. So there's a parabola that would have 1 minus 3i and 1 plus 3i as its roots. Check it with quadratic formula. If you graph that, where would it cross the x-axis? Yeah.
Wouldn't it cross the x-axis on the real number?
Yeah, it wouldn't cross the x-axis. It would be shifted above it in this case. Any questions on that? There'll be a problem very similar to that on the test. All right, so homework tonight, 138, 9 through 13, 15, 19 through 22, and then just jumps around a little. 25, 27, 32, 36, 39, 40, 47. Okay, don't forget, I will be after school for extra help today. So if you need to come in, I'll be here. And then we'll go over this right before the test tomorrow. And then we'll have the rest of the time to do your test.